Hello everyone, how are you? So today we are going to start our new chapter, Electromagnetic Induction. Very interesting chapter. Try to understand every topic of this chapter, because this chapter is very much important as well as interesting. So I will explain every topic in details, and further if you face any difficulties anywhere, then share with me. So the first thing is that let us try to understand what is magnetic flux. Chapter is your electromagnetic induction. Electromagnetic induction. Why this is electromagnetic induction? What is the concept of this electromagnetic induction? We will explain everything in details, but before that, to understand it, it is very much important to understand what is magnetic flux. Magnetic flux. Magnetic flux. Yes, we are very much familiar with the term electric flux, and electric flux. We know electric flux. We know Gauss's theorem. Here we will understand the concept of magnetic flux, same as that of the electric flux. Electric flux, the number of electric lines of force crossing normally through any surface. No? Here magnetic flux, the number of magnetic lines of force, crossing normally through any surface. Means this concept of magnetic flux is introduced to measure the strength of the magnetic field at any point in terms of the surface area. In terms of surface area, we want to know the strength of the magnetic field at any point in terms of surface area and then magnetic lines of force. Obviously, that is the number of lines of force crossing normally through any surface held in a magnetic field. No? So let us try to understand. Say for example, this is your north and that one is your south. This is the north pole, and that one is south pole. Right? Now the lines of force from north to south emanate from north, terminate to south pole, like that. Now let us place this. This is the surface area. Suppose this is the surface area, and which is held perpendicular to the magnetic field. If I place like that or like that or like that, then it is not perpendicular. Here I am placing it perpendicular to the magnetic field, and the number of lines of force crossing through this surface normally is nothing but your magnetic lines of force. Now the problem is that if the surface area is not perpendicular to the magnetic field, then what will happen? You see, suppose this is your magnetic field. This is your magnetic field, right? And this is your any surface area. Suppose this is surface area, right? Now, the normal to this surface area, is, if the surface area is like that, the normal should be along this direction, correct now? If the surface area is like that, the normal is along this direction, yes. Normal is along this direction. And suppose it makes an angle theta with the direction of the magnetic field. With the direction of the magnetic field. Suppose its surface area is A, and normal to this surface area, which makes an angle theta with the direction of the magnetic field. Then magnetic flux phi, magnetic flux phi, yeah, phi m, sometimes written like that, magnetic flux phi m, yeah, phi, magnetic flux is equal to surface area into magnetic component of magnetic field into component of magnetic field normal to the surface area. This is your definition of magnetic flux. Another definition of magnetic flux. Magnetic flux is defined as the product of the surface area and component of magnetic field normal to the surface area. So, here surface area is A and component of magnetic field normal to the surface area. This is the magnetic field. This one is B cos theta and B sin theta. Na? So, you see, if this is like that, then this is your sine and this is your cos. This is B cos theta, B cos theta, B cos theta, A B cos theta. Yeah, A dot B, yeah, B dot A, B dot A. So, magnetic flux is defined as the dot product of magnetic field vector and area vector. Magnetic field vector and area vector. So, obviously, this magnetic flux is a scalar quantity and it is the dot product of magnetic field and area vector. Now, the problem is that if the surface is like that, any shape, suppose, let us take an elementary part, elementary area dA, then magnetic flux phi is equal to integration of over the surface B dot dA vector, right now. B dot dA is the surface area of an elementary surface, so B dot dA, right. So, this is your concept of magnetic flux. I repeat it again. The magnetic flux is introduced, the concept of magnetic flux is introduced to measure the strength of the magnetic field at any point in terms of magnetic lines of force. And this magnetic flux is defined as the product of surface area and component of magnetic field normal to the surface area. So, your surface area is A and component of magnetic field normal to surface area is B cos theta. That is why AB cos theta means dot product A dot B is equal to AB cos theta, means AB cos theta or BA cos theta, no issue, B dot A. That is, you may define magnetic flux again in like that. Magnetic flux is the scalar product of magnetic field and surface area. Right? Understand now? Understand? So, let us now see the units and dimensional formula of magnetic flux. So, let us see the spatial cases. First of all, spatial cases. Spatial cases. Number 1, if theta equal to 0 degree, if theta equal to 0 degree, phi is equal to BA, cos 0 is 1. If theta equal to 90 degree, right, cos 90 is 0, phi is equal to 0. If theta equal to 180 degree, 180 means cos 180, right now, like that. You see, on in last class some students asked me how it is, sir, the result. So, I am showing it here. See, BA cos theta, right, BA cos theta, cos 180, cos 180. So, cos 90 plus 90, right. So, 1 into 90 odd multiples of from cos to sin, and it is your first second quadrant, right. So, minus 1, understand na? Understand, cos odd multiple, so it is cos to sin, and it is second quadrant में second quadrant sin and cosec are positive, and sin and cosec are positive, and so as it is cos, so it is negative, minus sin 90 means minus 1. So, it is Fi is equal to minus BA. So, anyway, if the surface area is in such a way that the normal makes an angle 0 degree with the magnetic field, if the normal makes an angle 0 degree with the magnetic field, means this surface area is perpendicular to the magnetic field and we are getting the maximum number of lines of force. Yes, this is the fact. This is the fact. You see, if I keep the surface area like that, this is surface area, if we put the surface area like that, then I will get maximum number of lines of force. Then the magnetic flux is maximum only when the normal makes an angle 0 degree, your surface area makes an angle 90 degree with the field. If normal makes 0 degree, means surface area is perpendicular. फिर से बोलो, if the surface area is perpendicular, what is the value of theta? It is 0 degree, because here I am talking about the angle with respect to normal, not with respect to surface area. So, if the normal makes an angle 0 degree with the field, means surface area is perpendicular, and if the normal makes an angle 90 degree with the field, then the surface area is parallel. If surface area is parallel, then the normal is along this direction. If the normal makes 90 degree, surface area is parallel. So, you don't be confused. I am repeating it again, that if the surface area is parallel, then the area vector is normal to the magnetic field, and if the surface area is perpendicular, normal is this is area vector is parallel to the direction of the magnetic field, right. Understand? Understand? So, the thing is that SI unit and dimensional formula for this magnetic flux. Let us see the SI unit and dimensional formula of magnetic flux. So, SI unit and dimensional formula of magnetic flux. SI unit of magnetic flux. SI unit of magnetic flux. So, magnetic flux phi is equal to B A, simply, yeah, B A cos theta, B A cos theta, or if theta equal to 0 degree, phi is equal to B A, right. Now, we see B magnetic flux, if B is equal to 1 Tesla and A is equal to 1 meter square, then phi is equal to Tesla meter inverse, which is known as 1 Tesla meter inverse, which is known as 1 Weber. 1 Weber. So, SI unit of magnetic flux is Weber, and the magnetic flux is said to be 1 Weber, right. Magnetic 1 Weber is the magnetic flux. 1 Weber is the magnetic flux through a surface of 1 meter square. 1 meter square surface area, right. When the magnetic flux crossing, magnetic field lines are crossing normal to it, right now, in a magnetic field of 1 Tesla. 1 Tesla magnetic field, surface area 1 meter square, then your magnetic flux is 1 Weber, right. I repeat it again, 1 Weber is the magnetic flux through a surface area of 1 meter square when crossing normally through a magnetic field of 1 Tesla. 1 Tesla magnetic field, lines of force are crossing normal to the surface area of 1 meter square, then the magnetic flux produced by it is 1 Weber. Now, dimensional formula. Phi is equal to B A, already we know F is equal to Q B B, no? Then B is equal to F by Q B into A, F by Q B into A, F is M1 L1 T minus 2, L2 area, Q is AT, B is LT minus 1. So, M1 L3 T minus 2, then A minus 1 L minus 1, ultimately it is M1 L2 T minus 2 A minus 1. This is the dimensional formula of magnetic flux. Okay. Now, let us try to understand the term electromagnetic induction. Electromagnetic induction. What is this electromagnetic induction? Very interesting. Try to understand. Electromagnetic induction. Let us see the term first of all. Electromagnetic induction. Electromagnetic induction. Three terms. electromagnetic induction. If there is any change in magnetic flux, there is a generation of induced current. If there is any change in magnetic field or magnetic flux, there is a generation of induced EMF and hence current. That is electromagnetic induction. Let us try to understand. Let us do one experiment. Let us consider a coil, and this is your galvanometer. A coil. So, number of turns are there, right? So, as there is no current, the galvanometer shows no deflection, galvanometer showing no deflection, right? Now, you see, let us do one thing. Let us take a bar magnet. This is a bar magnet. Suppose this is the north, this is the south. Let us bring a bar magnet close to the coil. That is, coil is in the field of this magnet. Coil is in the field of this magnet. So, the lines of force is like that, right? Maybe like that, not to south, not to south, not to south, not to south, north and south. Now, you see, here also like that. Now, we see, if we move the magnet towards the coil, the magnetic flux linking the coil will change. You see, B is equal to 0. Suppose I am not changing the position of the magnet. So, whatever the magnetic field, magnetic flux linked with the coil will remain same, right? If there is no change in the position of the magnet or coil, that is, both are remain at rest, there is no change in magnetic flux linked with the coil. Linking means what? If the coil is far away from it, that is, the magnetic flux is not linked with the coil. These coils are far away from the magnet. But if this coil is placed in the magnetic field of the magnet, means each turn of the coil is linked with the magnetic field, flux, right? So, magnetic flux linking the coil. Here we call the magnetic flux linking the coil will remain same, because there is no change in position of magnet or coil. Now, let us do one thing. Let us move this magnet towards the coil. As I am changing the magnet towards the coil, there is a change in magnetic flux linking the coil. And as there is a change in magnetic flux linking the coil, there will be a deflection in the galvanometer. And if there is a deflection in the galvanometer, which simply indicates that there is current, there is induced EMF, there is induced current, there is induced EMF. And this generation of induced EMF in a coil or conductor, whenever the magnetic flux linking the coil or conductor changes, is known as electromagnetic induction. I repeat it again, try to understand. Electromagnetic induction is the phenomenon by virtue of which there is a change in, by virtue of which there is a generation of induced EMF in a coil or conductor, right. Whenever there is any change in magnetic flux linked with the coil or conductor, there is a generation of induced EMF in it. Understand now? So, I repeat it again, the phenomenon of production of induced EMF and hence induced current in a coil or conductor. Whenever there is a phenomenon of, I repeat it again, the phenomenon of production of induced EMF and hence induced current in a coil or conductor, whenever there is any change in magnetic flux linking the coil or conductor. Simply, if there is any change in magnetic flux linking the coil or conductor, there is a generation of induced EMF in it. Understand now? This is your electromagnetic induction. Now, same, if you move the magnet away from the coil, if you move the magnet away from the coil, there also change in magnetic flux linking the coil, there also generation of induced EMF, but deflection will be in opposite direction. Means the direction of induced EMF depends upon the change in magnetic flux, whether increase in magnetic flux or decrease in magnetic flux. We will see it in Lenz law, right. So, the thing is that very simple, if there is any change in magnetic flux linking any conductor or coil, there is a generation of induced EMF, there is generation of induced EMF and hence induced current. Understand now? Understand? Any doubt? Any doubt? Okay. Chalo. Now, flux linkages. Let us try to understand what is flux linkages. This is your electromagnetic induction. We will see the direction of later electromagnetic induction. Flux linkages. Flux linkages. What do you mean by flux linkages? Flux linkages is the product of the number of turns and the flux linked with each turn of the coil, that is N phi. N phi is the flux linkages. Flux linkages is the product of the number of turns and the magnetic flux linked with each turn of the coil, that is your flux linkages. Now, let us go to our Faraday's laws of electromagnetic induction. 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 So, to describe this phenomenon of electromagnetic induction, that there is a generation of induced EMF and hence induced current due to the change of magnetic flux. To explain this phenomenon, Faraday introduced two laws. One is Faraday's first law and another is Faraday's second law. Number 1, Faraday's first law, and then Faraday's second law. Faraday's second law. Faraday's first law, Faraday's second law. So, according to Faraday's first law of electromagnetic induction, according to Faraday's first law of electromagnetic induction, if there is any change in magnetic flux linking with a conductor or coil, there is a generation of induced EMF, and this induced EMF lasts so long as the changes continues. I repeat it again. According to Faraday's first law of electromagnetic induction, if there is any change in magnetic flux linking with a conductor or coil, there is a generation of induced EMF, and this induced EMF lasts so long as the changes continues. মানে যত সময় পর্যন্ত চেঞ্জ হবে তত সময় পর্যন্ত ইনডিউসড ইএমএফ হবে, আর চেঞ্জ যদি স্টপ হয়ে যায় তাহলে আর ইনডিউসড ইএমএফ জেনারেট হবে না। ভেরি সিম্পল। আবারও বলছি, whenever যখনই there is a change in magnetic flux linking with a conductor or coil, there is a generation of induced EMF, and এই induced EMF থাকবে কত সময়? Last so long as the changes continues. মানে এইটা হলো আমার কয়েল আর এটা হলো আমার ম্যাগনেট, আমি এই ম্যাগনেট মুভ করছি, ইনডিউসড ইএমএফ জেনারেট হবে, আমার হাতের মধ্যে ইনডিউসড ইএমএফ জেনারেট হচ্ছে, আর once I'll stop this magnet, there is no change in magnetic flux linking with the coil, there is no induced EMF. Induced EMF is 0. Induced EMF is so long as the changes continues, আর চেঞ্জ বন্ধ তো ইনডিউসড ইএমএফ ও 0. Understand now? Now, as this induced EMF is due to the change in magnetic flux, obviously we have to relate this, how much induced EMF will generated due to how much change. Second law will give the magnitude of induced EMF. According to the second law of Faraday's second law of electromagnetic induction, the induced EMF generated in a coil or conductor is directly proportional to the rate of change of flux linkages. Rate of change of flux linkages. সাপোজ আমার এই কন্ডাক্টরের, সাপোজ এইটার মধ্যে ইনিশিয়ালি ছিল n phi1, n নাম্বার অফ টার্নস, and phi1 হচ্ছে ম্যাগনেটিক ফ্লাক্স। নাও আই এম মুভিং দ্য ম্যাগনেট টুয়ার্ডস দ্য কয়েল, and finally its flux linkages is n phi2. তো চেঞ্জ ইন ম্যাগনেটিক in time dt, in time dt n phi1 to n phi2, the magnetic flux changes. If the magnetic flux changing from n phi1 to n phi2 in time dt, then your induced EMF is directly proportional to n phi2 minus n phi1 dt. Right? I repeat it again. According to Faraday's second law of electromagnetic induction, the induced EMF is directly proportional to the rate of change of magnetic flux. Rate of change of magnetic flux linking the conductor or coil, or E is equal to K and d phi dt. K is a constant of proportionality, and I will take it outside. Phi2 minus phi1 is d phi dt. K is equal to 1 is equal to n d phi dt. K constant of proportionality is 1, n is equal to E is equal to n d phi dt. This is your second law. Now interestingly, another thing is there. Let us see the direction. The direction is given by Lenz, Lenz law. So the direction according to Lenz law, the direction of induced EMF is in such a way that it opposes the cause. যে ওকে ক্রিয়েট করলো, ক্রিয়েট করার পরে ওই আবার কজকে অপোজ করছে। The direction of induced EMF is in such a way which opposes the cause. Try to understand. মানে যে ক্রিয়েট করলো এই ক্রিয়েটরকে আবার ও অপোজ করছে। This is very familiar to us because আমরা যে সাপোজ একজন মানুষকে তুমি খুব আদর করে ভালো ইয়ে করে তুমি ওকে বড় করলে, এরপরে ওই ওকে তুমি মানুষ বানিয়ে এরকম করলে, আবার ওই তোমাকে যদি অপোজ করে, হ্যাঁ কিরকম লাগবে? সো এখানে এটাই হচ্ছে, ইনডিউসড ইএমএফ হলো কিসের জন্য? চেঞ্জ ইন ম্যাগনেটিক ফ্লাক্স। আবার এই চেঞ্জ ইন ম্যাগনেটিক ফ্লাক্সকে অপোজ করবে কে? ইনডিউসড ইএমএফ। দ্যাট ইজ direction of induced EMF is always in such a way which opposes the cause. মানে opposes the cause হলে এইখানে হয়ে যাবে একটা মাইনাস সাইন, E is equal to minus n d phi dt, right? And this is your Lenz law. So this is let us explain this Lenz law in details. Let us try to understand. See, if the magnet is moving towards the coil, the induced EMF generated here, এইখানে যেটা induced EMF generated হলো, it has a tendency to oppose it, and যদি অপোজ করতে হয় তাহলে এখানে এইটা নর্থ, তো এইটা হতে হবে নর্থ, আর এইটা নর্থ হতে হলে, এই থাম নর্থ হতে হলে কারেন্ট হতে হবে এই দিকে। Understand na? If the current is along this direction, then only this is north. So as the magnet is moving towards the coil, the direction of induced EMF is in such a way that this end becomes north. Right now. Now if the magnet is moving along this direction, suppose, or away from the magnet, and as it is moving away from the magnet, it is a tendency, stop it, ধরো এটাকে। তো ধরতে হলে এটা কি হতে হবে? সাউথ, রাইট না? সো এটা যদি সাউথ হতে হয় তার মানে এটা নর্থ, তার মানে কারেন্টটা হতে হবে এই ডিরেকশনে। আন্ডারস্ট্যান্ড না? অ্যাজ দ্য ম্যাগনেট ইজ মুভিং এওয়ে চলে যাচ্ছে, তো ধরতে হবে, তো ধরতে হলে এটা নর্থ, তো এটা কি হতে হবে? সাউথ। ধরলো, সাউথ দিয়ে ধরলো, তো সাউথ হতে হলে কারেন্টটা হতে হবে এই দিকে, এটা হতে হবে নর্থ, রাইট না? আর যখন whenever the magnet is moving towards the coil, যখন towards the coil যাচ্ছে, বলবে আসিস না, আসতে দেবে না, স্টপ ইট, এন্ড স্টপ করতে হলে এটা কি হতে হবে? নর্থ হতে হবে। আন্ডারস্ট্যান্ড না? দিস ইজ that is at every time it is opposing the cause, opposing the motion of the magnet. Okay, so let us see this Lenz law in details. Lenz law in details. Lenz law. Try to understand this Lenz law. Lenz law. Let us consider three cases. A magnet, a coil, galvanometer, north, south. right. Magnet is at rest, B is equal to 0. As magnet is at rest, the galvanometer shows no deflection, current is 0, induced EMF is 0. Now you see case 2, case 1, case 2, let us consider case 2. Is magnet, say magnet south north, galvanometer. Now you see so if the magnet is moving along this direction towards the coil, if the magnet is moving towards the coil, then there will be as magnet is moving, there is a change in magnetic flux, and as there is a change in magnetic flux, there is a generation of induced EMF. Now, what is the direction of induced EMF? The direction of induced EMF is in such a way that it opposes the cause. Opposes the cause মানে ম্যাগনেটটা এদিকে মুভ হচ্ছে, ইনডিউসড ইএমএফ বলবে না আসিস না, দ্যাট ইজ as the magnet is moving towards the coil, induced EMF has a tendency to stop the magnet, and if it want to stop it, that if it is not, then it should be not, and if it is not, to make it not, if thumb is not, then the current is along this direction. Very simple, right? Now current is like that. Galvanometer will show deflection, right? Galvanometer will show deflection. So as the magnet is moving towards the coil, there is a generation of induced EMF in such a way that it opposes the cause, and to oppose the magnet, this is north pole, and this, to make it north pole, the direction of current is like that, induced EMF accordingly. Now consider the case 3. Case 3. This is my magnet, say magnet north, south, consider a coil, now as suppose here the magnet is moving away from the coil like that along this direction, as the magnet is moving away from the coil, there also change in magnetic flux linked with each turn of the coil, and as magnetic flux linking the coil changes, there is a generation of induced EMF, and this induced EMF always has a tendency to oppose it, that is, as the magnet is moving away, then it has a tendency to stop it. যে ধরে রাখা, and ধরে রাখতে হলে এটা হতে হবে সাউথ, and এটা সাউথ হলে হতে হবে এটা নর্থ, and এটা নর্থ হতে হলে থাম্বের দিকে হতে হলে কারেন্ট যেতে হবে এই দিকে, so current should be along this direction, current is along this direction, right? Galvanometer will show deflection along this direction, right? Now so you see আগে কারেন্ট গেল এইদিকে, এখন কারেন্ট গেল এইদিকে, that is the direction of induced EMF and hence current is totally depends upon the change in which direction the change is going on, or right now in which direction the magnet is moving right now, and as the magnet is at rest, there is no change in magnetic flux, there is no generation of induced EMF. As the magnet is moving towards or away from the magnet, there is a generation of induced EMF, and hence there is a change in magnetic flux, and hence there is induced EMF. And direction of induced EMF depends upon the direction of the magnet, motion of the magnet. Here depends upon the change, in which কি চেঞ্জ হচ্ছে, ইনক্রিজ হচ্ছে না ডিক্রিজ হচ্ছে, right? Understand this is case 3. Now you see this, that is simply according to Planck's law, the direction of induced EMF is in such a way that it opposes the cause, right? Opposes the cause মানে এ যখন ক্লোজে যাচ্ছে তখন ক্লোজে যেতে দিচ্ছে না, আর এ যখন এভে যাচ্ছে তখন ওকে এভেও যাচ্ছে যেতে দিচ্ছে না। দ্যাট ইজ মুভিং টুয়ার্ডস, তো বলে না, আবার এভে তখনও বলে না। দ্যাট ইজ ইট অলওয়েজ অপোজেস দ্য কজ, দ্যাট ইজ দ্য ডিরেকশন অফ ইনডিউসড EMF. Understand? Now this is in accordance with the law of conservation of energy. This is in accordance with the law of conservation of energy. How? If the magnet is at rest, then there is no change in magnetic flux, there is no generation of induced EMF. Now, as magnet is moving towards the coil, there is a generation of induced EMF which opposes the cause, and as it is opposing, then I have to do certain work done to move it. Suppose for small displacement dx, I have to do certain work done, because আমি যখন এটাকে নিয়ে যেতে চাইবো, then I have to do certain work done against the force of repulsion, not repelling. Then I have to do certain work done right now against the force of repulsion. Same displacement dx k, whenever the magnet is moving away from the coil, then also I have to do certain work done and same amount of work done. মানে যতটুকু ওয়ার্ক ডান এদিকে নিতে লেগেছে আবার আনতে গেলেও সেম অ্যামাউন্ট অফ ওয়ার্ক ডানই করতে হবে। দ্যাট ইজ অ্যামাউন্ট অফ এনার্জি যেটা, এটা কি হয়ে গেল, কনজার্ভড হয়ে গেল। দ্যাট ইজ Planck's law is in accordance with the law of conservation of energy. Understand now? Understand? Any doubt? Okay. Chalo. Now, interestingly, one thing is that why I am only telling you that if there is any change in motion of the magnet, there is a change in magnetic flux linking with the coil. Why not whenever coil is moving towards or away from the magnet, there is also generation of induced EMF হতেই পারে। আমি ম্যাগনেটকে স্টপ রাখলাম, কয়েলকে মুভ করালাম, also there is a change in magnetic flux linking the coil, there is a generation of induced EMF and it is known as motional EMF. কি বলা হয়? motional EMF. যেমন সাপোজ ধরো, ভেরি সিম্পল, এই রুমটা হচ্ছে ম্যাগনেটিক ফিল্ড না, এটা হচ্ছে আমার নর্থ আর এটা হচ্ছে সাউথ, এটা কি নর্থ আর ওটা কি সাউথ। নাও আই এম এ কন্ডাক্টর and I am moving in this magnetic field, and as I am moving in this magnetic field, the magnetic flux linked with me is changing, and as the magnetic flux linking with me changing means there is a generation of induced EMF, and hence there is a generation of induced current, and that is known as motional EMF. কি বলা হয়? motional EMF. Let us see what is this motional EMF. So motional EMF means there is a generation of induced EMF in a coil or conductor whenever it is moving in a uniform magnetic field. Whenever there is any motion of the conductor or coil in a magnetic field, there is a generation of induced EMF which is known as motional EMF. motional EMF. বুঝতে পারলে? motional EMF. See, hey hello, this is my, suppose this is north and this is suppose south. Try to understand. this is south, then obviously the magnetic field is like that, north to south. Magnetic field lines are like that. Right? Now, in this magnetic field, suppose magnetic field is B vector. Try to understand. Let us consider a uniform magnetic field along this direction. মানে ছাদ থেকে সিলিং থেকে গ্রাউন্ডে এই ফ্লোরে আসছে in this way. Right? Now, let us do one thing. A conductor of length L, এইটা মার্কারটা, try to understand. A conductor of length L moving along this direction, moving perpendicular to the direction of the magnetic field. এই হলো একটা কন্ডাক্টর। কন্ডাক্টর টপ ভিউটা দেখাচ্ছি, মানে ট্রাই টু আন্ডারস্ট্যান্ড, এই পোর্শনটা দেখাচ্ছি। কন্ডাক্টরটা তো এই মুভ করছে। এই কন্ডাক্টরটার টপ ভিউটা, কন্ডাক্টর এইদিকে, কন্ডাক্টর লেন্থ কত L। সো এ কন্ডাক্টর অফ লেন্থ L মুভিং অ্যালং দিস ডিরেকশন, এই ডিরেকশনে গেল, অ্যান্ড ফাইনালি কন্ডাক্টরটা এই জায়গায় গেল। কতটুকু ডিস্টেন্স ট্রাভেল করলো dx in time dt. Suppose the conductor moves from the point A to the point B, covers a displacement dx in time dt along this direction, right? Velocity v. So let us consider a conductor of length L moving normal to the magnetic field with a velocity v vector, covers dx distance in time dt. Then you see length is L, cover course a distance dx. Then what is the area covered by the conductor in time dt? Area covered by the conductor, area covered by the conductor in time dt is L is equal to L dx. Understand na? L is the length of the conductor and cover করলো dx distance. See, এটা হচ্ছে L length আর এটা হচ্ছে dl distance cover করলো, তো এরিয়া L into dx না, L into dx. So L length dx distance cover করলো, এরিয়া কতটুকু, এরিয়া covered by it is, surface area covered by it, surface area, area covered by it is L dx. Therefore magnetic flux is equal to BL dx. Right now magnetic flux, because magnetic field into area, L dx is the area. Right now magnetic flux is equal to BL dx, magnetic flux. Now you see magnetic flux, suppose magnetic flux d phi is equal to B magnetic field into L dx, a magnetic field into area. Now differentiating both sides, or d phi dt is equal to BL dx dt, differentiating both sides with respect to t, or d phi dt, d phi dt means change in magnetic flux, right now, is equal to d phi dt is equal to BL V, dx dt means V, right now. So if there is already, we know d phi dt, E, what is this? E, already for a single turn, here number of turn is 1. So actually we know E is equal to d n d phi dt from Lenz's law, only considering the magnitude. So E is equal to n d phi dt, but for a single conductor n is 1, so it is d phi dt, d phi dt is E is equal to BL V. So induced EMF is equal to BL V whenever the conductor is moving normal to the magnetic field. But the thing is that not necessary সব সময় কন্ডাক্টরটা নর্মাল টু দ্য ম্যাগনেটিক ফিল্ড মুভ করবে, বাট একটা জিনিস, কন্ডাক্টর যখন মুভ করবে, মোশনে আসে, তখনই ইনডিউসড ইএমএফটা হবে। That is, this EMF is only because of the motion of the magnet, that is why it is known as motional EMF, and once this velocity is 0, then induced EMF is 0, then induced EMF is only because of the motion of the conductor or coil, and hence it is known as motional EMF. Now you see, if the conductor is not moving normal to the magnetic field, it is moving like that. Suppose in this direction, it is moving in such a way that it makes an angle theta with the direction of the magnetic field. At that time, what I have to do? I have to consider the component perpendicular to the magnetic field. Then component perpendicular to the magnetic field I have to consider, and at that time V sin theta. If theta is, as it is, if theta is equal to 90 degree, whenever it is moving perpendicular to the magnetic field, theta is 90 degree, then it is PLV. Understand now? Understand? So this is your motional EMF. Motional EMF माने आज के in this class very important two things are there. If there is any change in magnetic flux linked with a coil, means if there is any motion of the magnetic field या magnet या current carrying conductor, or if there is any motion of the conductor in a magnetic field, means by any means if there is any change in magnetic flux, there is a generation of induced EMF, and this is your electromagnetic induction. So this electromagnetic induction have lots of applications. Lots of applications are there. Today's electrical devices, lots of electrical devices based on this electromagnetic induction. We will discuss lots of applications on our next class. You see, if you face any difficulties, because this chapter is very important and very interesting chapter, I am repeatedly telling you that interesting, and take it interestingly. If you find interest on any subject, any topic, then it will be helpful for us, then it will be easy for us. Sometimes we may oftenly call that physics is quite tough. The tough is only whenever you take it with less interest, you find less interest. So thank you very much for listening me. If you face any difficulties anywhere, share with me. Okay, bye.